Hi, the 13.2 Logistic Regression for binary y. So now that we discuss estimation, so how to estimate parameters. So in a linear regression model, basically the way to estimate the beta is to minimize the summation of epsilon I square. So that is the summation of basically, okay, so if, summation of the y minus beta naught minus beta 1x1 minus up to beta p times xp, beta p times xp and square. So we minimized this quantity, and this is pretty straightforward in the sense that this is a quadratic function of beta naught to beta p. So it's the multivariate version, but basically we are just finding the minimum of the quadratic function, such as x squared minus 3x in maybe the beta, but the beta square minus 3 beta. So it's pretty straightforward. And actually, if we differentiate it, then this becomes a linear equation for beta, and we can solve it. So everything is linear algebra. But the logistic regression, we have the link function f. Okay, so at least it's more complicated than usual. So we think about actually the f inverse, but the f inverse of the beta naught plus beta 1x1. Okay, suppose we only have one term, but this is really complicated function of beta naught and beta 1 if we include f inverse. And we use the concept of MLE, the maximum likelihood estimation, which we introduced in chapter 11. So for linear regression, the MLE is the same as least square. So it's not really useful to know that anyway, that we use least square. But if we have more advanced model, then we should go back to the MLE. Then what's the best estimator? We should think about it. So MLE is really the important concept when we generalize the regression model, linear regression model. Okay, so now we think about what's the maximum likelihood function for the logistic regression model. So let y be the response and let x be the predictor in matrix form. And say we let xi be the ith row of x, so just ith observation. Then the likelihood function for this ith observation is equal to this pi I if yi is equal to 1. So success probability is pi 1. So if we succeed, then likelihood is that probability. Okay, so suppose success probability is 0.8, and actually we succeed, then likelihood is 0.8. If success probability is 80% and we failed, then likelihood is 0.2, so 20%. So this is the likelihood function. Or if we use the f inverse, the pi I is f inverse of xi beta, and the 1 minus pi I is 1 minus f inverse of xi beta. Okay, then the log likelihood function, the log of likelihood function for all observations combined is log of this one. So the product over all i's of f inverse of xi beta. So here, the f inverse of xi beta is for yi is equal to 1. So we think about the all I which satisfies yi is equal to 1, and we take the product. And for I with yi is equal to 0, we have to multiply this quantity. Since we take logarithm, we can make this the summation. So basically, we want to maximize this quantity. And actually, this is much more complicated than the multiple linear regression, the optimization. And actually, we cannot really solve this by linear algebra. So we have to rely on numerical method to maximize this likelihood function, number 2. But actually, the good thing is that actually this function is convex in terms of beta. So it's not quadratic function, but conceptually, okay, so suppose we have beta 1 and beta 2. and we have some surface of the L of beta naught and beta 1, then actually it's convex. So we have actually this isn't really convex, right? So this is convex. It's not the as simple as the parabola, but it's convex. So we can monotonely the approaches to the true solution. So actually we can have the monotone sequence of increasing the likelihood function. So usually we don't have problem to go to find the maximum. Yeah, and to be exact, this procedure is done by so-called reweighted least square method. So this is a kind of the sequential method that using similar to the least square. But anyway, so we don't cover that material, but the point is that we have to numerically optimize it, and that there is still a good way to find the solution. And in R, if you want to optimize something, you can use also the optimum function. So this is the general function to numerically optimize some function.